Thank you very much for joining us for our next Groundwater Modellers Forum webinar. I'm delighted to welcome Alistair Black to present this. For many of you, I'm sure Alistair will need no introduction. Alistair's been in the hydrogeology industry for about almost 20 years now, partnered with Emmett Foster Wheeler, SRK, and now in recent years he's been running his own company, Groundwater Science, which is, I understand, been growing from strength to strength. Alistair has been behind many codes which have been used and loved across the industry, such as SWACMod, surface water modeling, flow source, and his name is attached to various of the resource models as well. On the Groundwater Modellers Forum committee, he's been a valued member, done lots of work keeping us going, keeping us connected, bringing the wider network together and giving us lots of wise advice. And so I'm really looking forward to hearing what Alistair has to say to us today. I'm sure it will have a big impact on our decision making in the near future. Just if I can ask for video cameras to be turned off while Alistair's presenting, just to protect his network. I think most of you, apart from me, have done that. And without further ado, I will hand over to Alistair.
Hi folks, Happy New Year, and I'll just share my screens and then I'll turn off my own camera. I think just so you can just see the screen itself. One moment. Hey, can you see my screen? Somebody, Christopher?
Yes, I can.
Brilliant.
Thank you.
Okay, and oops, just minimizing all this stuff. Super. Okay, so this talk is on why river low flow recovery at times might be less than the reduction in abstraction. And it's examples from several intermittent rivers. There's been several last-minute redactions and areas where we've had to make anonymous different locations. So it doesn't have quite all of the examples I was hoping to bring in, but I think we've got three good case studies which are showing a pretty consistent picture. But I'll start off with this word intermittent. So I don't know if Mike Price is on the participants lists, but might want to say something. I had a very well-reasoned email sent saying we are misusing the word ephemeral. So I'm going to try very hard to use the word intermittent instead of ephemeral or winterborne. So I think if there's going to be any wise advice coming out today, it's probably going to be this slide number 1. So it is highlighting that ephemeral is not best used for non-perennial situations, which is what I've been using up to date. Sorry about that. So it's apparently ephemeral is more about surface runoff and rainfall events and very localized and very short-lived, whereas really the non-perennial parts of the river, the episodic stuff, should be intermittent streams. So Mike, I don't know if you're there or not, or if you want to say anything at the end, but if there's anything further you want to add, then I think this is probably a great time to help anybody else who's having the same mistake that I was. So otherwise, I'll leave it to the end. I've only got 30 slides here, so much less than I normally use, and we definitely don't need the hour or so to go through those. There's lots of time to discuss as we go through it at the end. Okay, so what actually is the problem that we want to present today? We have select instances where stream flows don't appear to improve following abstraction reductions. I put select very much in italics there because I'm certainly not suggesting that sustainability reductions don't work or anything like that, just that there are a few instances where there's been this conundrum that we haven't had an improvement in low flows specifically that we were expecting. And critically, really, it's models that have been used to help motivate what abstraction changes should be. So there's been an expectation which hasn't necessarily come to pass. So this piece of work is trying to look for commonalities between the select instances that we're aware of, where the yield hasn't necessarily improved in the river, and think, if this is a genuine issue, where does that unabstracted water go? In near every case, the abstractions are very near the river, in the centre of a catchment. So where else would the water go, if not to the river? And then if models are suggesting that there should be an improvement to low flows, but there hasn't been, does that mean that we've got some form of deficiency in our management decision tools? I'm not necessarily referring to models here in the sort of mod flow numerical model sense, although that's most of what this presentation is on. It could also be spreadsheet models or GIS style models. So this slide I'll spend a bit more time on because it's the format of most of the graphs that come in the rest of this presentation. So this is taken from a real example. And if I can just explain all the various different details that are on this graph to start with. It's a flow duration curve. So just for the fullness of everybody watching, a flow duration curve, instead of looking at a time series of river flow, we're looking at the exceedance time for a particular flow rate. So for example, if you look in the x-axis at 70% exceedance, that black line is showing 20 megalitres per day. So we're saying 70% of the time, this river is flowing more than 20 megalitres per day. At 50%, this river is flowing more than 30 megalitres per day. So it's a way to summarise a time series graph that's quite helpful for what we're looking at today. So this black line, that is effectively our observed flow at a gauge. So that is our baseline. And we've got two models here, the solid lines. The first is a very simple model, this grey line at the top. If we turn off a well, and in this case it's 14 megalitres per day, this simple model assumes that 14 megalitres per day all goes to the river. So really we're expecting that black line to jump up by 14 megalitres per day. The other model that we have is a mod flow numerical model, and it's the purple line, and that's showing in the low flow period a bit less than what that grey model was predicting. But there is still an increase in the low flow period. All of that is on the left-hand axis, so the total flow of the river. The right-hand axis is always for the dashed lines in these plots, and what we're looking at there is the difference between the purple and the black line. So that right-hand axis, the dashed line, is the change in flow. I'll put that because some of the examples later on, there's very small differences and you can't see it just from all the overlapping lines. So effectively it's showing that we've got about 8 megalitres per day increase in flow being predicted at that low flow time period of the river. But the problem here that we're trying to investigate, the conundrum, is it's not apparent that that 8 megalitres or 14 megalitres or whatever actually appeared in the river during low flow time periods. So why not? If anyone's ever get any questions, stick up your hand or turn on your microphone or whatever. Thanks. So it's hard to discern what the benefit in reality actually is, or has been, or could be. In the reviewed cases, at least the ones I'm aware of, there has been a real lack of monitoring data before any abstraction change. In most instances, there's good data after the abstraction change, but not before. So it's quite difficult to say a cause and effect and be definitive. The other real challenge is weather and climate, different things, obfuscate the abstraction change signal, especially when we're looking at whole river catchment scale rather than just like a borehole single location scale. So weather and climate really do complicate, come back onto that later on. or make it hard to see if there actually has been the expected benefit. Now, this is not a new issue. It's something that various water companies have brought up, and also a couple of large farms who have brought up this same issue in the last several years. Also, there was a paper, a poster that was presented at the Groundwater Modelling Forum that Affinity and Adam Taylor led, which is on a very similar topic to this as well. So there is several bits of work that are being done on it. It has been discussed over various years. So multiple mechanisms have been posed as to why we're not getting this uplift in flows. One is aquifer storage, that the aquifer holds water over time. We just haven't seen the full effect of that change yet. Another is riparian losses. So as water table rise with abstraction turnoff, we get more loss of water to the atmosphere through evaporation. So not all of that water then reports to the river downstream. Anisotropy, so in particular, geological layering, impediments to flow, particularly vertical flows, has been something that's received a lot of attention in the last several years. And similarly, it's been posed that there should be the ability for more water to flow effectively under a river in the very near surface. And that's potentially bypassing the gauge, we don't notice it. So these are things that have been suggested so far to date. And I'll come back onto those in just a moment. But we've got 6 examples. Not all of them are presented in this slide set. We've got 3 examples here, mostly for confidentiality reasons. It's quite a contentious issue in some locations. So 5 of those are headwaters, so the upper part of the catchment. So it's very much within the intermittent stream flow reaches. In all of those cases, the abstraction is close to the stream, and the general catchment in that area has got at least single-figure meter relief, normally tens of meters worth of relief along the area of the cone of depression of the abstractions. One of them is a bit of a standalone. It's within the perennial parts of a stream. It's close to a wetland. It's still fairly close to the stream, and it's as flat as you can get in that particular area. You can probably guess where that is. So I'll come back to those in a moment. So storage, I'll just very briefly touch on. I don't think it's relevant in the examples that we're looking at here. The cone of depressions, they're all within the chalk. They're that standard, very wide, shallow cone of depression. And critically, when the abstractions are turned off, they show a very rapid recovery. And we're talking about within weeks for the water to be recovered. And depending on what time of year they get shut off, it could be much less than that. So I don't believe that storage is a main answer to this conundrum. The riparian option, I think, is relevant to one of the cases, that perennial reach one, because there's a large wetland nearby, and at least in the way that it's modelled presently, in that case, 2/3 of the water that is turned off in the abstraction, so there's an increase in the evaporation simulated in the model by 2/3 of the volume of the abstraction that's turned off. So that's quite a substantial loss of water that would have otherwise have reported to the river. But I think that's a special case here. So I think that counts for the perennial, and I didn't really want to discuss that one any further. So I'm removing that example from the collection that we have. So anisotropy, layering, and the active stream connection frequency. So the ability for groundwater surface water interaction and the distance from the perennial reach is effectively what follows for the remainder of the presentation. Okay, so far too much text up until now, so it's a bit more figure-based, pleased to know. Okay, so we're looking at abstraction impacts near intermittent streams. If we can start off just explaining the plots that we're looking at. So the top is high groundwater level conditions, the bottom is low groundwater level conditions. And the blue contours are the simulated water tables drawdown associated with a well. So that's our conant depression effectively, or drawdown. The red areas, that is showing the losing of stream flow to the aquifer under the pumped conditions. So the top under the high water table conditions and the bottom under the low water table conditions. And the crosses are just showing the perennial limit on the bottom and the top of the intermittent stream in the top plot. So that area in between is dry across the dry period, the low groundwater level periods. So the main thing to take from this plot is that in this example, we've got a 7 kilometre long intermittent reach, or up to 7 kilometres. The head change associated with that abstraction is generally of the scale of 10 centimetres to about half a metre for most of the area of that conant depression, at least most of the area of the stream interaction. The topographic relief across that area is quite a bit more. It's metres scale. That's important for how much of an effect that has on how much of the river becomes active or activated by the rise in groundwater associated with the abstraction turnoff. And in this case, there's up to about 400 metres of river that in theory may be re-wetted on account of abstraction reduction of that 7 kilometres intermittent reach. So all the rest of that is effectively the change associated with recharge, seasonality, regional water level conditions that are really controlling that 7 kilometres of moving from perennial up to the very top of the river on the most extreme years. So this plot that I showed at the start is from that exact same example. So that's the dry and the wet spatial, and this is the time series or the flow duration curve equivalent. Now, it's the exact same plot that we looked at before with the purple and the black and the grey. And that purple line, I can say now that's the ModFlow 1996 model and the prediction of 8 megalitres uplift and flow in the low flow period. The green line, the solid green line, is the flow duration curve that is predicted by a research model, effectively. This is a ModFlow 6 model of the same area. So as you can see here, the increase in low flows is much lower in this prediction. And if you look up at the high flows, there's more water being predicted. The difference between the low flows and the high flows works out to be mass conservative. So the 14 megalitres per day is still almost all going to the river under all 3 of these different models, the spreadsheet model, the ModFlow 96 model, and the ModFlow 6 model. All of them have got effectively 14 megalitres per day going to the river, but the timing of that is changing. So under the ModFlow 6 model, this dashed green line is showing that there's almost nothing going in at the bottom, and that's gradually increasing until about Q70. Beyond Q70, it's pretty similar, the 2 models, and then at the very top end, we've got more water coming in again in the ModFlow 6 model. That grey line, that's just a flat 14. So curiously, this is showing that the 2 ModFlow models, especially the ModFlow 6 models, actually showing more than the abstraction switch off going into the river during the high flow period and quite a bit less in the low flow period. I believe, so this particular run was a few years ago that was done. I believe this is the first instance of having a highly non-linear response to abstraction reduction in intermittent rivers, so showing that minimal uplift in the low flows. I think I'd said everything that was on that one. So the key question here is, what's the difference? What's the difference between the purple run and the green run? So the green run, that ModFlow 6 model, different code base, but that's relatively irrelevant here. There is much more calibration to the behavior of winterbournes. So there's a lot more calibration to there's much more calibration to accretion profile spot flow data. There's increased spatial resolution along rivers. So instead of having a 200-meter grid, we've got a 20-meter or 50-meter model cell spacing. And the result of that is that we've got more gradation of the groundwater, surface water active area. And there's also more layering within the chalk. I'll come back onto that in a bit. I was thinking if there's anything else you need to add in. Recharge as well. There is enhancements to the recharge, but I don't think that's relevant to this discussion. I think probably most people will have seen images like this, but it's just to give a flavour of what we're actually talking about with these different styles of grid. So that bottom left-hand cutout image is showing the higher resolution that you can put in along the rivers. So you can get 20-meter or 50-meter resolution along that stream, as opposed to the coarser cells that don't necessarily align with streams in rectilinear grid models. And the other big change between the runs is the layering styles. So most of the ModFlow 96 models, they either use 1 or 2 layers, where it's trying to represent an active part of the chalk in the upper levels and a more passive, deeper part of the chalk. And a lot of the models of the last few years have been more multi-layered. So typically layered based on lithostratigraphy to give the ability of vertical impediments to flow, be that marrow bands or whatever else. But that doesn't stop us additionally over the top of that having some of those more geomorphological controls on transmissivity of the chalk, so you can superimpose the same sorts of details as we had in the chalk models with fewer layers, but with the added advantage of more vertical impediments to flow. So the top left picture here is a leapfrog geology model that's developed for the area. The bottom is the ModFlow numerical implementation of that geological model. And the right hand is the strat column and what's been used to define the layers. In this case, there was a 9-layer model, but that just was silly. So 5 layers was enough to get the effect that we're looking for. So that was the first example. The second example is quite short, and I will bore you by saying pretty much exactly the same thing. It's quite deliberate. We tried to find the same situation in another county. So just a couple of slides here. So this is the high level conditions, looking at a spatial plot of simulated stream flows. So blue is effectively a flowing stream. Grey is dry. So those green crosses at the top is the effective top of each one of those tributaries under the high water level conditions. And if we switch to the low water level conditions, so just really showing us the size of the intermittent reach in this case. And the final figure on this example, exactly the same as before. In colouring, the purple is the ModFlow 1996 model. The green is an adapted model that's been really specifically built for representing accretion in this area as well as we can. And the solid lines here, the flow duration curves, they're not very helpful because they're all lying on top of one another, so it's probably best just looking at the dashed lines. So we've got that grey line, it's the uniform change by a spreadsheet model. We get a little bit of a response in the purple, showing a bit less abstraction reporting to the river in the dry period in that Modflow 96 model, but quite a marked reduction in water reporting in the low flows in the Modflow 6 model. So the difference in Modflow 96 models and Modflow 6 models are pretty much identical in this example as they were in the previous one, two completely different models, but the changes, the evolution of those two models was quite similar in style, where we've got higher spatial resolution along the rivers, change in layering style. In this case, there's a more significant evolution in the recharge, but again, that's unrelated. I think probably this model, it has had a great deal of calibration time put into accretion and looking at flow and no flow events, and the data set was excellent, really, for spot flow data and trying to understand what was wet and what wasn't when. But the main point is that we are still effectively mass conservative. All of that water does go to the river, but the timing of it is very much biased towards the high flows, even though it's a uniform abstraction. This is a single slide, and I put in here just to remind myself a point to make. It's related to the past example, and it's just say all years are very much not the same. So we've been showing things where we've got high water level conditions and low water level conditions. These are the extremes, and the figures that we're looking at here, the two top images are accretion profiles stacked through time. So a little bit, you can't see the details between them, but the y-axis is the distance from the gauge at the bottom to the top of the river, and the x-axis is through time. So each one of those blue to red bits, the colouring is effectively showing the flow in the river. So it's many accretion profiles as we go to the right. And the reason for bringing this up was just that some years we've got the full wetting up of that river, and other years it stays dry for most of that intermittent reach area. So if we're thinking about the storage that has increased within the aquifer because of the reduction of abstraction, and that water only reporting to the river when that river becomes active, then not all years are going to receive that, so we can get a lot more water in some years, or vice versa. The bottom plot is the difference between two scenarios. You can't see the difference between the two plots at the top there. So that's showing the uplift in flows and whereabouts you might get uplift in flows across that historical period from an abstraction change. And moving on, it's just a side comment. This is the final example, and unlike the other two, this one's completely synthetic. It's wholly made up just to have a bit of a cleaner demonstration of different timing impacts dependent on where we happen to be within a river stream. So on the next image, I'm going to show 4 time series. So 4 changes in flow passing through the gauge. One's going to be in the bottom, on the right-hand side. So that's the perennial, fully flowing perennial area. Then the green one is going to be just upstream of the perennial limit, and then moving further up the river as we go. So they're all in the same graph, so we can see them all at once. So that orange line is pretty much a uniform increase in river flow when this synthetic 5 megalitres per day abstraction is turned off. The next one up is the light green. So we see a similar pattern to what we saw before, but a bit more subdued. The dark green is the next one. So we see a much more pronounced pattern of low flows and dry in the lowest point of the flow. And then the blue one is a slight exception because it's near the model edge. And in this exceptional case, not all of the abstraction turn-off reports to the river. Because of how far it is up the catchment, some of that is going to the scarp slope to the west. And that's why it's lower than the dark green line on the left-hand side. So in that case, not all 5 megalitres per day reports to the river, but in the other runs, they do. So I'll stop talking for a moment, just let you get your eye in on the difference of those shapes. Okay. So just coming to the end. So what does this really matter? Winterborne abstraction influence can be improved with some of the recent changes in modelling. Some of the styles will give us the ability to more gradation along the river and make it easier for us to use calibration data, use spot flow data, build these accretion profiles. Multi-level piezometry is not something we've had very much data for, but I think that could be something that could be helpful for further work. There's very few instances where we've actually got data that can help on that. So finer resolution along the river certainly has helped in a couple of our models. But the more significant one that I was wanting to come on to is when we're using tools that have an assumption of a uniform abstraction is turned off, and therefore there's a uniform uplift in flow to the same value. And I think in most cases, it's an absolute fair assumption, but in Winterbornes, especially if we get a bit of a distance from that perennial limit, I think we can start to move into difficult territory. And we've now found in multiple counties models that when we do have abstraction switch-offs in the upper parts of catchments, then we can have quite different impacts throughout that flow duration curve. So some of the numerical models are presently not set up to represent that temporal bias that I've been presenting. I think several of them are. So the EHCC model, Test-Nitron model, Kennet, this variegated chess, which is a research model. There's an Anglian demonstration model. I'm sure that's not an exclusive list. I think all of these are quite capable of doing this. I think some of them may benefit from more calibration to accretion data, but all of them should be able to represent what we're presenting here. But some spreadsheet models or GIS style tools, I think, probably make assumptions that we might want to review. Probably won't say more on that. But coming to the questions that were posed at the very beginning. So are there commonalities between the areas where we're seeing a less than anticipated flow improvement? Generally, yes, in these upstream areas. So exclusive to the Winterbornes. And the bias is that we are seeing the water flowing to the rivers, all the water flowing to the rivers, but it's going into the high flow periods, and surprisingly, we're getting more flow in the high flow periods than we would have been from the abstraction itself. I think everything else I've said there, I'll maybe just leave that slide up, and I think I'd rather just leave this to discussion time rather than continuing on. So it's a very wordy presentation because there's an expectation, I think, for some of these slides to be sent out and for it to be standalone. So I'll press escape in that and open it up for questions.
Thanks very much, Alistair. It's really informative. Yeah, as I say, plenty of time for discussion, so please go ahead with your questions. I think there's a hands up button, but you're welcome just to call out your name if you're feeling brave. Or you can put questions in the chat to be read out.
There you go. Oh, hi there, Mike. Sorry, lots of distractions going on in the background there. So I think I can see Mike Street with a hand up.
Yeah, hi, Al. Thanks for that talk. I think perhaps it might be useful to separate two issues we've got here. One is how good are our groundwater models at predicting low flows and changes in low flows in response to changes in abstraction. And that's something that you've talked quite a lot about. But I think the other aspect is really that, you know, conceptually, what is going on? Why is it that, you know, a sort of simplistic approach would be that you've got constant rate abstraction, most public water supplies are fairly constant rate, you turn it off, you know, the flow change in the water balance should be about the same. And I think that, you know, the fact that we're seeing differences in different aquifer settings, and, you know, we do see this in the permatriassic as well as the chalk, but maybe not quite as an extreme. You know, so it's a, you know, I think that we should talk about the conceptual aspects of this, which is what are the aquifer properties that make this happen and where might we expect it to be worse. And I think that probably I would guess that it's something to do with aquifer diffusivity, you know, some combination of transmissivity and storage, and that where those diffusivity is high, you might get more exaggerated effects. And so I think that would be something useful to focus on.
Yes, good. Okay, thank you. That's helpful. So you've made me realise that there's quite a significant thing I probably neglected to describe in this presentation. So I think the main finding in what we've reviewed so far is if the abstraction in question is a distance upstream of the perennial limit of the stream, the head rises with the shut off of abstraction, obviously, but we're not seeing any real change in stream flow at that time, because that head change isn't nearby connected to the stream. But once the stream starts to advance up the catchment again, and once it becomes part of the, once we get groundwater surface water interaction activating as that stream grows, then it can get the benefit of that extra storage, that water table rise that happened sometime earlier in the year, which is why we're getting more water reporting to the river than the value of the abstraction during the high level periods, and very little or none in the low level periods. So at least in the examples that we've been looking at, it seems to be the frequency of the river being connected to the groundwater system in that cone of depression or form of cone of depression.
Yeah, thanks. I would say that this, you know, what we're saying is that these groundwater systems, the river groundwater surface water interaction is fundamentally non-linear, and the amount of non-linearity is probably related to some aquifer properties, which, yes, maybe not just diffusivity, there could be some geometry aspects as well, but I would flag up diffusivity as a factor to think about, and that, you know, those things can exacerbate the problem. But, you know, if we have well-calibrated models, the point of well-calibrated models is they should get around the problem. But we shouldn't be surprised that this is a real effect. It's not a modeling effect, it's a real effect.
Well, absolutely. It's come about from the observation that there doesn't appear to be an increase in flow after actual shutoffs happened, and then the whole conundrum of why wasn't there? Where did the water go? So yeah, for sure. I think maybe some of the difficulties in some of the model build styles have resulted in an inability to represent what we're looking at here, which has led to a more uniform uplift in river flow throughout the flow duration curve.
Can I flag James Dodd's question? It may be related. James, do you want to present it, or shall I read it out for you? He says, the modelling seems to be reliant on poor calibration data, flow, accretion, vertical head distribution. How much could this be contributing to error? I wonder if that needs some qualification, but I don't know if you know what he's getting at.
Maybe. Yeah, I wondered about putting in calibration. I don't want to make the presentation too long. I've got really bad colds, you can probably tell. So I tried to make the presentation shorter. At least in one of the models that we're showing there, I think the calibration is really very good. Where we've actually got surprisingly good accretion data sets. But then that model is being designed specifically for representing this kind of system. I'm trying to think how to respond.
Well, where I was coming from, you mentioned a couple of times, Al, that there was poor flow data or poor accretion data, and maybe I misheard you because I'm doing three things at once. But and I just wondered whether that was contributing it. My experience is river flow data is not very accurate, and I've rarely seen. Well, spot gauging is. I'm not sure how useful spot gauging is, and I've rarely seen accretion data collected, other than for possibly a research project or a very specific purpose, but widespread accretion data
it can be variable for sure.
Incredibly rare.
Yeah, I think what you're picking up on is probably the catch-all statement at the very beginning, actually, that at least in the instances of this phenomenon I've been aware of, there hasn't been very good data before any switch-offs. So to actually be conclusive on the effect of a switch-off has been really rather difficult because of that. So I think that's definitely an issue. And I agree, yeah, the accretion spot flow data can be very variable in its quality. I think one of the models that we're presenting here, I think, has got pretty good data quality that I think is very helpful in understanding where the river is dry and when. But as a generality, I'd certainly agree that spot flow data can be very variable, whether it's measured by ultrasonics or a Satsuma or whatever else.
Thank you. I think Tim was the first to have his hand up of the people in the group. Can we turn to you, Tim?
Hey, great. Thanks very much. Yes, I just wanted to comment that, of course, most models are carefully designed to be mass balanced. Therefore, I would expect your modeling results to balance out quite nicely. And I suppose what that means, therefore, is if these lack of increases in stream flow actually balancing those reductions in abstraction, it sort of comes back to Mike's comment about any gap between the numerical representation, or based on the conceptualization, and the actual setup, and therefore the potential for other losses to occur in reality which just aren't being represented. Does that make sense?
Yes, I think so. So a couple of responses there. The examples that were given are mass conservative. The contrary thing that we found in the last few years, I'll look at this in different areas, is that we might not be getting the amount of water that we're hoping to get under the low flow conditions, but then we're getting a compensatingly more amount under the high flow conditions. So what we're not getting at the time that we need it, we're getting at the time that we don't necessarily need it. So whether it's a 14 megaliter or 1 megaliter abstraction that's been turned off, that is ultimately still the amount it reports to the river, just not necessarily at the time that we want it. There are some other details at play in some locations. So in one of the examples, the abstraction change wasn't reporting to the stream. It was being evapotranspired away, at least part of it was being evapotranspired away by wetland features in the way that they're being represented in the model. But I think those are local issues. So I think that the main point I was trying to communicate in this talk was the reduction in low flows, the reduction again in the low flows and the corresponding increase during the high flow period. Did that answer your question, Tim?
Yeah, I mean, I guess so, but I mean, I can see that temporally and spatially, it doesn't exactly balance out. You know, there's a shift in time and space, perhaps, and as you say, it's not what we're actually hoping to achieve by these interventions. But are these, because ultimately, are these real mass discrepancies? You know, if you sum it over a year, for example, rather than instantaneous differences, which, as you've pointed out, can be explained by these shifts in space and perhaps time. I mean, you were saying you reduce the amount of abstraction, but you don't see the corresponding increase in river flow. So is that actually a real loss of water somewhere else, or is it just shifted in time and space and comes out in the end?
Comes out in the end.
Areas?
Yes, exactly what you said at the end there. Yes, comes out in the end. And in most years, it comes out within that year. It's as the intermittent river migrates up the catchment, then more of that river becomes actively connected to the groundwater environment, and more of that increased head will then manifest as water flowing to the river. So it's a temporal shift, as you described in the end there.
Okay, that's good. That makes sense. Thanks.
Thanks, Tim. Sue, can we move to you? Do you want to introduce yourself as well? I should have said beforehand. Do you have a question, Sue?
Sorry, yes. I've popped a question in the chat.
Oh, cool. There's a sort of different Sue.
Sorry, a different Sue.
There's a different Sue who got her hand up. I don't know if you're not on two devices, but you have put a question in the chat, so we might as well go with this one. Why don't you read it out anyway, Susan? It'd be better coming from you.
Is it just a fact of variable aquifer properties in the very near surface zone, which is maybe what Mike is alluding to partly, and whether if you have a particularly solution enhanced zone around your ephemeral water table, that could explain things, or maybe not. Anyway, just a question along those lines.
Thinking, one moment. I should expect in this case not. So if we're to take one of these Mod 4.6 models, got quite high spatial resolution, so it gives us the ability to design in these sort of quite precise features. You could draw in a high transmissivity corridor, try and connect up with the river very readily. But I think we'd still see the exact same issue, that we would get groundwater rise in that general headwater catchment that would turn off the well, and we just see the groundwater levels rise. And that groundwater level rise wouldn't manifest to extra river flow until the river actually moved up into that area. I'm sure you could push a bit more water into the river, but I don't think we'd ever get to the point where we've got turn-off abstraction and the full volume reports to the river straight away. I'm going around in circles a little bit here, but I think the main thing that we're trying to investigate was this conundrum of why aren't we seeing the water in the river at the time that we're expecting to see it? And these model runs were the outcome of trying different scenarios of ways to actually have a model that showed this conundrum rather than showed a fairly uniform uplift in flow. So all the models prior to this were showing that we would get a good improvement in low flows, but that didn't manifest in reality.
Got lots of questions to get through, it looks like. Rolf, can we turn to you?
Yeah, I suppose I'm going back to James's comment a bit, and just wanting to make the observation that in the past with our Environment Agency regional groundwater models with a sort of 200-metre grid resolution, the representation of surface water groundwater interactions sort of felt a bit abstract, or maybe impressionist if you're a bit more optimistic. And so we've now been moving towards ModFlow 6 models and a much finer resolution at the streams, and that kind of means, I think, that we have the opportunity to look at what the model output is showing us and then go back to the actual real world and maybe do some spot gauging to try and improve the calibration that way, which in the old models, I don't think it would have really worked. And we're also starting to think about sort of citizen science type stuff where maybe you send people out and they don't record flow, but they might tell you where the actual flowing parts of the streams are, and I think we can feed that kind of information back in. And it just sort of feels to me like we do have a lot of opportunities here with the new models, where we do have to go through a process of going back to the real world and getting some actual real data to sort of prove these points. That's it.
Yeah, I agree. And just how even if it is not as good data, it's just a binary. Is it flowing? Is it not flowing? That's very helpful in model calibration. Be able to line those particular pieces up. So I reshared the screen here, and so that purple is the 200-meter resolution ModFlow 96 model, and the green is the ModFlow 6 model. They are both showing this same sort of feature of less than the grey line at the low flow and more than it in the high flow. So both the ModFlow 96 one and the ModFlow 6 one, they're both doing the same thing. Like it is doing it, but with that extra spatial resolution and concentration and calibration to accretion in this particular model, we get a much more pronounced effect on that green line. And the reason I was wanting to do this talk is I want to have 5 different examples all showed effectively the same thing between these green and purple lines. That it doesn't really matter what county it is, all of these winter boards are responding in the same manner. Sorry, excuse me, a bit of a head cold, lose my voice as well. But yeah, no, absolutely, I agree. And this model that we're looking at here has benefited from citizen science studies of going out and getting more data to aid that calibration effort. And there's work in HNL in using these plots and bringing that sort of accretion data into these images to help in understanding seasonality of the intermittent reach.
Well, thank you. Phil Hubbard has a question. Do you want to read that out, Phil?
Yeah, can do. So yeah, given that we seem to be seeing evidence of recovery more at high flows than at low flows, and that, as Mike said earlier, this isn't just in winterbournes, but also in the sandstone, where you might not get the temporal effect, but you do see water coming back in further downstream where you don't need it, rather than the headwaters that are stressed. It does seem that abstraction reduction is often a very inefficient way of getting water back into these streams. So a question for whoever would like to answer it is, should we be doing more augmentation rather than abstraction reduction?
I'll leave that one to somebody else to comment on. The only thing I'll say is what I've been looking at here has been very specifically looking at the more extreme cases, which have been chalk winterbournes.
As a thumbs up from Mike Streetley.
I will leave that to somebody else to comment on augmentation.
Thumbs up from Mike Streetley. Anyone else got a comment on that? Put something in the chat if you want to say something on that. Jane Dottridge.
I think Adam had his hand up first, but
Oh, yeah.
as I am sort of semi-retired, I come across more and more of the local pressure groups, chalk stream lobbies, who probably won't believe any of this, but I've got a question on whether the vertical connectivity, the presence of mile bands, is a really controlling factor. And I'm thinking particularly because I had a conversation this morning about some of the scarp short rivers that pass, or dry streams, as they would comment, that pass over a lot of different layers of chalk in a very short distance, and whether this phenomenon is more likely to be more marked or less marked.
That's a really difficult question because when I started this off, I thought it was going to be more marked when we introduced more layering. And I think that giving us the ability to have that layering and more control over how the model was set up would make it easier for us to represent this oddity. I think, in honesty, in the run that it presented today, it's not been the controlling factor. The controlling factor has actually been the relative topography of the catchment and the seasonal recharge. What I hadn't shown in the slides is the growth of the river associated with abstraction change. In the examples that we've got, it's actually very small relative to the overall intermittent reach length. So I think the biggest one's a few hundred meters growth from abstraction switch off. And it's because like the cone depressions are tens of centimeters of head change normally under these chalk high transmissivity situations. So raise the water by 10 centimeters, how much of a river is that going to reactivate? But the recharge change seasonally is quite big. And the regional change in water levels can be meters, and that does then influence it. So I think actually in most examples that I've looked at, the biggest control has been the relative topography and the seasonal head variation.
Thank you.
We're officially
locally. I'm sure there's local exceptions to that.
We're officially at our time. I'm just going to take a moment to mention our next webinar, which is going to be from Adam, modelling beyond the boundaries from submodels to metamodels, and that's on Thursday, the 9th of February. So I've just put the details in the chat. Feel free to drop off if you've got something to rush to. I'll take a couple more questions because we can, and it seems a good moment to take Adam Taylor's question.
Cool.
Feel free to give a brief plug as well, Adam, if you want to be on next webinar.
Thanks for the plug. I might take a break actually because the baby's just started crying. So okay. I'll let someone else ask a question. Thanks.
Will the baby come to the webinar? I don't know. Okay, thanks, Adam.
Good effort, Adam. Good dad skills. But and Adam and Affinity have prepared a poster for the past Groundwater Modelling Forum, which is a very similar topic to this as well. So it's a different take on the same conundrum.
Just occurs to me to say that we are always on the lookout for more presenters as well. So if you'd like to give a presentation on anything groundwater modelling related, Doesn't matter how junior or senior you are, please do give me an email. I would love to hear from you. David McDonald, would you like to introduce your question? Or shall I read it out?
No, I'm happy to ask the question. I was just wondering, I didn't get a sense of whether are we talking about real examples of where abstractions have been ceased, and whether recognizing there are big issues with observations, whether still there's any anecdotal information that shows that, you know, what the modeling is telling you is what's actually occurring in reality.
Yeah, there's a few questions there, I think. So I had 6 case studies, and I think 3 of those are actually historical shutoffs. A couple of them are proposed changes. So it is a bit of a mix, and there are confidentiality issues, especially with the ones that are historical shutoffs. So we can't necessarily present the details of those ones, unfortunately. But I think the key message trying to present was it's effectively the same story that keeps coming up on each one of these, and we can model this oddity of not having our low flows recovering as much as we'd like to. And the second part of your question, I think, was about observed data. Sorry, would you mind repeating that?
I think it kind of just followed on from the first question. It was, you know, I think you've answered it. You've said that there are observations that show that the modeling results are the reality.
There's observations that have shown that past modeling, past sort of model-centric decision support hasn't necessarily gone the way that it was expected. So we've got model simulations where it's suggesting that there should be a rise in low flows, but that hasn't come to pass. And we're trying to understand why, and if there's changes to the style of how we do these models, specifically for this kind of location, how we should maybe change our models to not be in the same situation again.
Thanks.
Thank you. I had a question, Alistair, if you don't mind. It's just whether this raises any questions about our representation of a naturalized scenario, and whether we ought to be revisiting that. Whether Winterbournes are really perhaps a bit more flashy and had lower low flows than our models are suggesting.
And I think that's very linked to exactly Elias's comment that's just come up as well.
Yeah, okay.
Which, if I could just read that out, says, since the ModFlow 6 models have been able to better represent the lack of flow recovery during low flows compared to ModFlow 96, what would the implications be for the EFI calculations that derive the abstraction reductions? How different would the EFI be in each example? So EFI is something that's draped off the naturalized. So I think we're talking about similar things.
Yeah, that's fine. Yeah.
And yeah, it's a good point in the naturalized, Christopher. Thinking the EFI is certainly something that I want to point at, because like even if we keep the EFI as it is, then assuming a uniform impact through time, I think is potentially giving us erroneous outcomes. But change of the naturalized, yeah, I'm not sure. I think we need to come back to that.
Mm-hmm. All right.
But I think these findings, they probably do have more implications for the spreadsheet and water resource GIS style approaches, where we've got assumptions of uniformness. I think that's where it really does come to play.
Ilias, if you're happy, that's answered your question as well. I will say.
Yeah, that's fine.
Thank you. Thank you very much, Alistair. That was really interesting, and it's certainly plenty of discussion. And yeah, thank you again for all your contributions to Groundwater Modellers Forum in general. Looking forward to Adam's presentation next month. Please do join us then. Have a good evening, everyone.
Well, thanks, Gino.
Congratulations.
Cool.